In this video series, we are looking at comparing groups on a quantitative response variable using multiple linear regression. And in the previous video, we actually constructed the regression model and saw how the coefficients were related to the differences in means. We had a baseline group in which we saw the mean of the group as the intercept, and then we saw how each of the other coefficients was simply a difference in means from that group and the baseline group. So we really have looked at differences in means, and we looked at the coefficient of determination, that is the R squared for the model. But now I'd like to take this all a step further, and I'd like to move into the analysis of variance. Analysis of variance can be used to determine if the variation of group means is too large to be attributed just to individual variation. That is, we have individuals with different observed scores, and that's true within groups as well as across groups. For example, in our data, we have an individualist group, and there's variation of observed scores within the individualist group, as there are in each of the other two groups, the hierarchicalist and the egalitarian. So we have all that variation, and because of that variation, it's no surprise that the means of the groups are different. But the question becomes, can the means of the groups be attributed just to that individual variation, or is there something else at play? This is a question of separating the signal from the noise. There's a lot of variation in our data, but can we detect a signal that there's a difference in those groups? So the way we do that is to decompose the sums of squares total into the various individual parts. Sums of squares for group means that can be calculated around a grand mean, sum of squares of residuals that are calculated around individual group means. And then those sums of squares can be divided by degrees of freedom to provide mean squares, which we will talk about in a moment. But let's start with decomposing these sums of squares. So let me call back up my notebook. And let's go back here and remember that when we're talking about the explained variation, we're talking about the difference of the predicted mean, which is the individual group mean, from the grand mean. So for the individualists, for example, we have a mean of 38.96. And then the grand mean, let me go ahead in my little window over here in the console, let me go ahead and calculate what that grand mean is. That's 33.3. So the difference of 38.96 and the 33.3, that difference there would be the explained. And that difference explained is for every person. In other words, once I have that difference of the 33.3, well, actually it would be the other way around, the 38.96 minus the 33.3, that difference would be for each individual. So with each individual, we have an observed, we have a predicted, there's a difference between those. We have an observed, we have a grand mean, there's a difference between those. So we start with the difference between our sums of squares total is equal to, we take the difference between the observed minus the grand mean, and then of course we're going to sum up all the squares of those things. So that's our sums of squares total. Our sums of squares explained or modeled is the difference between the predicted minus the grand mean and squared, but it's done for every single person. And similarly, the sums of squares residual or error is the sum of the observed minus predicted, and it's done for every single individual. Now, if you remember, I put residuals and predicteds into my database here. And so we could go ahead and calculate the sums of squares for each person. We could calculate their contribution to the total sums of squares. So actually, their contribution would just be a square, and then when we add them all up, it would be sums of squares. So let's go ahead and create those and look at those. So coming back here to my notebook, I need a code chunk in here. So let me go ahead and create that code chunk. And so I'm going to, let's call these just deviations. We won't square them right now. We'll just create the deviations. So the total deviation, so I'm going to call it plain risk total, or tot dev. Okay, the tot dev is going to be, as I say right here, the person's observed score. So that observed score is just score minus the grand mean. So that's going to be the mean of the scores. And that will be their total deviation. Then for their model, the explain piece, the part that's explained by the model, remember what the model is doing is it's predicting for each person in a group the mean for that group. So that's going to be then the sum of squares model will be the predicted for that group, which is just going to be the mean for that group. So, and you might say, well, where are we going to get the mean for that group? Remember, let me show you again. Remember, it's right here. It's in the predicted. Okay? So that is the mean for the group. So we can get the sum of squares explained deviation, or I'll call it model deviation, so that explained and error sounds too much alike. So the model deviation is going to be plain risk predicted minus the mean for plain risk and then the error deviation is going to be the observed minus the mean minus the predicted, which would be the mean of the group. All right, so there's the three different types of deviations that we're creating. And if we go back and look at the plain risk, there I've created those. But now let's get the sums of squares by squaring those things and adding them all up. So now I'll go ahead and do this in a new code chunk. So now what I want to do is I want to sum up the squares of the total deviation. I want to sum up the squares of the model deviation. I guess call that plain risk model deviation. And I want to sum up the squares of the error deviation. And here we go. All right, so let's Let's note a couple things here. I'm going to go in my console window where I use it as a calculator. I'm going to do some adding. Let's take that second one, the model deviation, 8292.854 plus 147,910.1, and that equals 156,203, which is the first number. In other words, we have decomposed that total deviation into the part that we can explain and the part we can't explain. Let's take a ratio of the part that we can explain, 8292.854, with the part, the total, that's 156,203, and that's 0.053. 0.053. Look back here. 0.053. That was the coefficient of determination. That is the portion of the total sums of squares we can explain. We can explain 5% of the sums of squares. So what we've done here is we have taken the sum of squares for group means, calculated around a grand mean, but did it for every person, all 225 people, did the residual, that is the difference between the observed and predicted, squared it, added them up, did that for the whole group, took those, squared it for each person, and then added out for the group, and that was a decomposition of the total sums of squares. Now, can we get this without doing those calculations by hand? Absolutely. We already had built the model. We already got a summary of the model, but now we can ask for an analysis of variance of the model, ANOVA, which is short for analysis of variance. And if I ask for ANOVA of the model, what I will get is all those pieces. There's the 8292.84 or 8293 when it's rounded. Here's the 147,910. It didn't show us the total here, but the total is just the sums of these two. Notice that the view, plane risk view, has 2 degrees of freedom. Why? We talked about that because it takes 2 dummy variables. It's a categorical variable with 3 levels. How many individuals did we have to start with? 225. When we get the total sums of squares, we have to calculate the mean, and therefore we lose 1 degree of freedom for that. So 225 minus 1 is 224, minus 2 is 222. That's the degrees of freedom that we have left for residuals. So the 222 plus 2 is 224, which is our total degrees of freedom, n minus 1. Back in your first stats course, you learned that was the total degrees of freedom because you had to divide that into the total sums of squares in order to get variance, or to take the square root of the whole thing and get standard deviation. So here also notice my p-value. We're not talking about inference yet, but I am showing you that the calculation here is the same one that we found here. And we'll talk more about this F statistic later, 6.223, but we see it here. But the next thing that we need to do is talk about mean squares. And so I'll talk about mean squares in the next upcoming video.